Okay, we've defined discrete random variables. Let's do something with them. Specifically, let's take some averages, okay? Or what we're going to call expected values. All right, well, say you have taken some quizzes and your scores were 9, 10, 9, 6, and 7. You want to know your average score. How do you compute it? Well, you know how to compute it. Just add up the 5 numbers and divide by 5 because there are 5 total. What do you get? In this case, 41 over 5, which is 8.2. Okay, so we all know how to compute averages, and what we want to do in this video is define a probabilistic notion of averages for random variables. So the expected value, which we write e of x with a line through it here. So you'll notice just like the probability measure had a second line through it, the expected value notation has another line through it. So expected value e of x of a discrete random variable x is just defined by the following formula. So it's just the sum of x times the PMF summed up over the range of x. Okay, so what I'm doing is I'm taking the possible values of x, I'm weighting them by their probabilities, and I'm adding that all together. Okay, so the difference is in the usual notion of average, I just add up all the numbers I have and I divide by the total number of entries, whereas here I add up all the possible values I could see and I weight them by their probabilities. Okay, well, there are a lot of ways that people refer to this expected value. So sometimes people call this an average or a mean or the expectation. I didn't write that down. And we sometimes denote it by mu sub x. Okay, so there are a lot of different ways people talk about it, but they're usually just referring to the same thing. Okay, how should I think about this intuitively? So let's say that probability is mass, okay? That maybe just for the right now, think of it as mass. Then the expected value is going to be the center of mass, okay? So that's what it actually corresponds to, all right? And as we're gonna see, this is a really important idea for working out many, many different concepts. But for now, we're just thinking about it as averaging for random variables. Let's go back to our example. So this is from the previous video, so it just sort of jumped onto the slide. Let's remind ourselves what it is. So before we get into the average, we roll 2 4-sided die. All the outcomes are equally likely, and we're interested in the sum of the rolls. And in the previous video, we worked it out. So we had this PMF that starts at 1 over 16 for seeing the sum being 2. It goes up to a 4th for seeing the sum being 5, and it goes back down to a 16th for the sum being 8. Okay, so what I want to know here is what is the average value of the sum? Okay, well, before I go any further, maybe we can just guess it by looking at this plot. And I can see that the plot is centered on 5 and symmetric, so I think the average should be 5. And let's see if that holds up with the formula. Okay, so I plug in this formula, so I sum up over the range x times the PMF. Okay, so that's going to be 2 times 1/16, right? So I went to this table and I got the value 2. I multiply it by 1/16, so x times the PMF. Next entries, I'm going to get 3 times an 8th, plus 4 times 3/16, plus 5 times a 4th, plus 6 times 3/16, plus 7 times an 8th, and then finally plus 8 times a 16th. Okay, so let's kind of add up everything together. We'll have it all over 16, so it's 2 plus 6 plus 12 plus 20 plus 12 plus 6 plus 2 all over 16. So we have one denominator that's 80 over 16, and now, okay, we see that that's 5, and that's great. We expected to see 5. That was our expectation. Sorry for the pun. And so that's exactly the center of mass on this plot. Okay, so that's kind of what we wanted to see with our intuition, right? So there's the center of mass. Makes sense. Okay, let's do another example, which is not so symmetric. Okay, so we're going to just change it up a bit. In this case, I'm going to just make up a PMF that's not going to be symmetric. Okay, and we're going to try to see where is our center of mass going to fall. Okay, so let's just say that I have, in this case, I'm going to have positive and negative values just to make it more interesting. Okay, so here I could have -1 or 0 or +1 or +2. And let's write the probabilities as in terms of sixth. Okay, so I'm going to have the probability of 0 being a sixth, +1 being 0, and +2 being a half, and finally -1 being a third. That adds up to 1. So the range in this case is just -1 0, and +2. Okay, before we go any further, the observation we can make is that we kind of expect that the center of mass for this plot should lie on the right side of 0, so it should be positive because there's more weight on +2, which also has a higher value, so it should be drifted a bit to the right. Let's work it out. So expectation of x is just the sum of the values of x over the range times the PMF. So that's going to be -1 times the PMF at -1 plus 0 times the PMF at 0 plus 2 times the PMF at 2. So that's going to be -1, looking at the plot, times a third, that's the value at that point, plus 0 times a sixth, plus 2 times a half. I got all those values from the plot. So I just get 2/3. Okay, so that's simple. Okay, and that's exactly as I expected. It's positive, so because +2 was kind of dragging it over to the right. The only thing that I'll kind of keep in mind here is that I'm just noting that the expectation here does not actually have to belong to the range of x, okay? So it doesn't necessarily belong to the range of x. It's the average value that I would see, okay? Meaning that if I ran this experiment and drew these random numbers many, many times and I average those values, I would expect to see 2/3 for that average, okay? It doesn't mean that on a specific draw I would see 2/3, but that the average value would be 2/3. All right, let's do something a little bit more application oriented. Okay, and we're going to talk about binary signaling, which is something you might see in the context of electrical or computer engineering. Okay, and so in this scenario, my experiment is kind of that I want to transmit a bit, so something with 0 or 1, and I want to send it over a wire. All right, and let's just take the model that the bit values 0, 1 are equally likely. And the way that I'm going to do this is to make it go over the wire, I'm just going to decide that the bit 0 is going to be mapped to voltage -1, and the bit 1 is going to be mapped to voltage +1. So then at the receiver, I can just look and see if I got positive or negative voltage, and that's how I'm going to determine 0s and 1s. Okay, so then the goal here is I have to both determine the PMF, okay, from scratch, and the average voltage. Okay, so this is a simple example where everything should kind of work out with intuition, but let's kind of work it out. So first of all, the two values the PMF can take are going to be, for x, are going to be -1 and +1. So the PMF value for -1 is calculated by looking at the probability measure for the bit being 0. And since the bits 0 and 1 are equally likely, that's one possibility out of 2, so it's a half. Same thing for the PMF at +1. That's the probability measure for bit 1, so that's going to be a half. It's 1 out of 2 possibilities. Okay, so I've worked out the PMF. I might as well plot it, and then from there we can kind of guess the average, and then we'll get it explicitly. So I'm just drawing +1 and -1 on my axes, and I'm going to draw the value 1/2, and now I draw my PMF. So I have a point of height 1/2 at +1 and another at -1. Okay, what's the average going to be here? Well, the center of mass clearly seems to be at 0 by symmetry, but let's just see if that works out from my calculation. So I take the expected value, I sum up x times the PMF over the range of x. So I have -1 times a half. So I got that from the -1 value in the range times the height of the PMF there, which is half, plus +1 times a half, and that's obviously 0, as I expected. Okay, we're just going to do this in a slightly more complicated way. So I'm going to talk about if I want to send 4 values, or rather 2 bits at once, okay? So I want to transmit 2 bits in terms of voltages, right? So I want to increase the data rate which I'm transmitting. And the way I'm going to do that is I'm going to transmit the bit sequence 0, 0 by the voltage -3, 0, 1 by the voltage -1, 1, 0 by the voltage +1, and 1, 1 by the voltage +3. Okay, so what I've been able to do now is I've been able to cram in 2 bits into a single voltage value rather than 1 bit into a voltage value. And depending on how much noise I have, this is kind of how I adapt how many bits I can send down a wire. Okay, so there's just a quick little application. And now I want to work out the PMF. Well, if I know that things are equally likely, so let's just assume that seeing any of these bit sequences as likely as any other, then it's going to be pretty simple. What I'm going to do is determine the PMF and the average voltage. And the PMF is just going to be, it's going to be a fourth. So I'm going to write it case by case when x is -3, -1, +1, or +3, and 0 otherwise. Okay, so I didn't need to go through this whole careful writing out of the probability measure because I see that things are equally likely. I see that there are 4 values, so then it has to be a fourth for each value, and I just write down the PMF from there. Now I can plot it, and so I'm going to get 4 points equally spaced, or sorry, not equally spaced because, yeah, they are equally spaced. My apologies. So they're 2 apart. It's just that my plot here is not quite to scale, but they're equally spaced, and they each have height a fourth. So there's one at +1, another at +3, another at -1, another at -3. And so what's the average value? Well, again, from the plot, the center of mass is going to be 0, and I'm just going to see that that's true. Okay, so I just calculate the expected value. I sum up over the range, x times the PMF, and I just plug in all these values. -3 times a fourth, plus -1 times a fourth, plus +1 times a fourth, plus +3 times a fourth, and that works out to be 0, as I expect. Okay, we could do more interesting examples, but the reason I introduce these is I'm going to reuse them as examples later in this video. All right, so with that in mind, let's talk about functions of a discrete random variable. Okay, so a function y is equals to g of x, so that's my function. I have this little g, which is the function applied to x, which gives me y. So, but the thing that's interesting about this is that the function is applied to a random variable. Okay, so x is a random variable here, and therefore the output of this function y is itself a random variable. Why is that true? Well, as we've talked about before, y of omega is just a composition of mappings, okay? So it's still mapping from the sample space to a real line. It's just that the mapping in this case is now the mapping x followed by the mapping g. That is the mapping for y. Okay, so it is a random variable, and so it's going to have a range and a PMF. And the way we can determine those is directly from the range and PMF of x along with the the function y of, which is g of x. Okay, so if I have these things, if I have the range of x, the PMF of x, and I have a function g of x, then I can work out what kind of random variable y is. So I can just plug in. So how do I get the range? Well, I just look at the set of g of x values for x in its range. Okay, this will be more clear through an example, so I'm just going to hold on to this formula till we do an example. The PMF value, I'm going to start with the definition. So it's the probability measure of the outcomes that map to little y. Okay, and now I can plug in for the mapping y using the thing that I've done above. So I replace y with g of x of omega, right? And now I see that what I'm doing is calculating the probability measure of the set of x that get mapped into y. And so what I can do, in fact, is just sum up the PMF of x for which the values are y when put through this function. Okay, so what does this notation mean before we describe this formula a little more? So this summation means that I sum up over the range of x such that g of x is equal to y. Okay, so meaning that if this y value I'm interested in calculating is +1, then I find all of the x values that once they pass through g, they end up being +1. Again, it's going to be easier to see how this works through an example. So let's do that. Let's go back to our binary signaling example. Okay. Right, so this is going to be binary signaling example. I put the PMF there. And let's say that y equals x squared is the energy that I expend in my transmission scheme. And what I want to know now is the range and PMF and average value of y. So the range of y, I can use the formula that I had before. So remember the formula said, take the set of g of x, so that's here going to be x squared, such that x is in its range. Here the range of x is -1 and +1. Okay, so what is this going to work out to be? I'm squaring -1 and +1. It works out to just be 1. So the range of y is now 1. At this point, things are pretty easy. If y only takes a single value, then all the probabilities on that value, so the height is going to be 1. But let's work it out explicitly to see it. the PMF at this one value is just going to be the sum of x such that g of x, in this case x squared, is equal to the value that I'm interested in this case 1. So I sum up the PMF values for that. So I get -1 plus +1 PMF values, and I get a half plus a half from the plot, which is 1, as I expected. So finally, the average should be pretty easy, but first let's draw the PMF of y, and then it'll be clear to see. So it's just a single point of height 1 starting at 1, okay, and that's just the simple PMF of y. And so the average value of y, again, I can use the formula for calculating expectation, and I'm just going to get 1 times 1, which is 1. Okay, so I mean, it's clearly centered at 1 because it only takes one value. Okay, let's make it a little more interesting. Let's go to this 4-ary signaling example. And I guess the point here is that to send these 2 bits using a single voltage, we're expending more energy. And we're going to see that explicitly. Here's the PMF for x. And so let y be x squared, the energy, find the range, PMF, and average of y. So we're going to use the same approach. We're going to take the range of y to be the set of g of x, here x squared, such that x is in its range, so -3, -1, +1, and +3, right? So what values can I now take? Well, the -3 and +3 get mapped to 9, and the -1 and +1 get mapped to 1, so I get 1 and 9 for the range of y. So what are the PMF values for 1? Well, I just sum up the x that get mapped into 1 when they pass through x squared, and I add up their probabilities. So I get PMF of -1 plus PMF at +1. So I get a fourth plus a fourth, which is a half, right? So the way that this works is you're combining values that map into the value of y that you're interested in. Same thing for probability mass function at y equals 9. So I sum up for the x that their square is 9. So what I'm going to do is add up the PMF of -3 because its square is 9 and +3 because its square is 9. I get a fourth plus a fourth, which is equal to a half. So drawing this PMF, I'm just going to get, this long now it's the y-axis, but kind of drawing this long axis to fit in all these points from 1 to 9. And so the first one is going to have height 1/2, and then I'm going to stay down at 0 for a while. So just have a lot of zeros in between, and then I have 9, again at 1/2. Okay, what's the average? Well, again, I can kind of stare at this PMF and decide that it's centered at 5, but I can calculate it explicitly. So it's just 1 times 1/2 plus 9 times 1/2, which is 5. Okay, because I've just summed up the values of y times their PMF, right, over the range of y. So I got 1 times a half and 9 times a half. So that's 5. Okay, so in this example, it turns out that the thing that we probably only cared about was the expected value of this function y. Okay, we did calculate the PMF and the range, but maybe those weren't the things that we actually wanted. Maybe I just wanted to know the average energy. The PMF and the range were just things I computed along the way. It turns out in these settings where I only care about the expected value of a function, so let's say e of y, then I can just use the PMF of x and the function g of x to get that expectation. I do not need to calculate the PMF of y nor its range. Let's see how that works. So take the expectation of y, that's the sum of y times its PMF, that's the definition. Now let's use the formula that we've already worked out for calculating the PMF of y. I'm going to plug that in. Okay, so here it comes. So I've replaced the PMF of y with the sum of the PMF values of x for x such that g of x is equal to y. If you go back a couple of slides, you'll see that was the formula. Okay, and now what I'm going to do, so this is kind of the trick, is I'm going to write in purple here that I notice that I can push y into the second summation, because in the second summation, I'm only dealing with the x values such that g of x is equal to y. Therefore, I can either write y there or g of x. They're the same thing in that particular instance as I've written in purple. So now I can just see that what's happened is that I've covered the whole range of x. I've just broken it up into two sums. And what I'm doing is summing up g of x times the PMF of x, right? And this is my nice, convenient formula for calculating expected values of y. Okay, so instead of going through this process where I first get the range of y, then get the PMF of y, and then finally get the average of y, I can just directly go for the average of y by plugging in g of x times the PMF of x. Let's do it on this example. I'm interested in the average value of y for x squared, so I'm summing up x squared times the PMF of x over the range of x, which is -1 and +1. Okay, so that's how it works in the binary signaling example. So that's going to be -1/2 squared times 1/2 plus +1 squared times 1/2, which is 1. And if you go back, that was the same answer we got through the long process. And you could do the same thing in the 4-ary case to get the value 5. We're not going to do that. Okay, another important property of expectation, which we're going to be using many, many times, is linearity. Okay, and what that means is that if I give you a random variable x and real numbers a and b that are constant, so these are not random, so x is a random variable, a and b are constants, then if I take the expected value of ax plus b, then that is a times the expectation of x plus b. So I can move a and b outside of the expectation, okay? And in general, I can't do things like this. Like if I had a square, I can't move the square outside of the expectation, but I can move linear functions in and out of expectations. Why is that true? Well, it goes back to the definition of expectation. So I'm going to use this formula, which we just developed, for calculating the expected value of a function. So what it said is I can plug in the function g of x, in this case, ax plus b, and multiply it by the PMF of x and sum up over the range of x. So I've just applied that definition here. Now I'm just going to break this up into two summations, one which is a times x times the PMF of x plus b times the PMF of x, okay? So if you look at the first line and the second line, you can see it's completely fine for me to break up the summation in this way. Nothing can go wrong. And I just recognize now that I have a times the expected value of x plus b times 1. Okay, and why do I have 1? Because of normalization. If I sum up the entire PMF, then I just have 1. Okay? So this is why linearity basically always applies for expectation. We'll see this many, many times over, but you should just assume that that's a nice thing that you have access to with expectation. Okay, so let's go back to our Fourier signal example and use this idea. So let's say I have y equals x squared, and we remember that we calculate e of y is 5. And let's say now what I want to know is z. What is z? Well, z is 3y minus 4. Who cares why that's the case? It's just some example that we're making up. And I want to know the expected value of z. So one thing I could do is go through some tedious calculations, or I could have 3 times the expected value of y minus 4, which is 3 times 5 minus 4, which is 11. So I just applied this formula that I had in the box up there, because it's a linear function. And the whole point of this is that I skipped a lot of tedious calculations about the PMF of z, and in fact, really about anything. I just reused things that I've already done. So that's the value of this linearity property. Okay, so now we're going to introduce a slightly different concept building on expectation, which is the variance. So the variance of x measures how spread out a random variable is around its mean. So variance of x is the expected value of x minus its mean squared. Okay, so let's unpack this a little bit. So I've written a lot of stuff down here, relative to the kinds of formulas we've had before. So first of all, let's get in a box. Let's just think about it. So on the outside, I'm taking a big expectation, and on the inside, I have a particular function. The function happens to be x minus its mean squared, whole thing squared, okay? That's just some particular function. So keep in mind that the mean is just a constant value, like 5 in that previous example. X is random. The mean is not a random number. So the mean is just a value. So it's fine to plug it in like this. And it might be easier for us to understand what this formula means by using a little bit more notation. Okay, so let's say that mu is the mean of x. Okay, so I'm just going to replace the expectation of x with mu of x. Now I write the variance of x as the expectation of x minus mu of x squared. Okay, And now I can think about this as the expected value of a particular function, which let's say it's y equals x minus mu x squared, okay? So this is completely fine to write down. And now I'm just going to try to justify to you through some examples why I care about this particular function, but it's completely valid to just write this down as a formula. We also define the standard deviation, sigma sub x, and that's just going to be the square root of the variance, okay? So once you calculate the variance, you can take its square root, you get the standard deviation, and sometimes we use the notation sigma sub x squared to denote variance, okay? And the reason we take this square root is usually to get things on the same unit. So if you imagine we had the units in volts, once I take the variance, I actually have volts squared in units. So the standard deviation is just pulling me back to the units of volts, okay? Before we do an example, let's look at a simple formula for calculating the variance of a linear function. Okay, so let's say that y is the function ax plus b, then what is its variance going to be? It's a squared times the variance of x. Okay, so this is a little bit different than the linearity of expectation property that we saw before. Let's see why that is. The variance of y is the expectation of y minus its mean squared. So now I'm just going to plug in for what y means in terms of x. So I substitute y for ax plus b. Okay, so I've done that substitution. And now I'm going to use linearity of expectation because I see a linear function in there. And I'm going to pull out a and b out of this inner expectation. So there they go. That's linearity of expectation. I'm free to do this. Okay, so now I'm going to cancel out the b's. I'm just left with ax minus a times the mean of x squared. I'm going to pull out a squared. So I'm going to pull a out of the inner square. And finally, I have a squared times the variance of x by definition. Okay, well, we've defined a lot of stuff. Let's go through a long example to try to get a little bit more intuition. Okay, so in this example, I'm going to draw some big table of PMFs. Okay, so my first PMF here, I'm just going to have some points that are going to take values on 0, 1, and 2. So at 0, I'm going to have, let's say, height 1/2. Okay, so let's draw that point. So I have a point at 1/2, then I have another point at 1/4 and another at 1/4. Okay, so that's my PMF for x. And I'm also going to have PMFs for y, which is 2x. Okay, so what is the PMF going to look like if y is 2x? Well, I'm going to have let's look at what happens to x equals 0. So 0 times 2 is 0. So I'm still going to have a value at 1/2 at 0. So that makes sense. There it is. What about at 1? Well, 1 is going to get multiplied by 2, and just going to be 2. So now it's moved over to the right. So I have a probability of 1/4 at 2. And again, I have 1 at 4. Okay, so the value x equals 2 moves over to be y equals 4. Okay, let's look at another PMF, which is going to be x plus 1. Okay, so z is x plus 1. So now everything's going to shift over by 1. So 0 shifts over to 1, 1 shifts over to 2, and 2 shifts over to 3. Okay, let's calculate the expected value for each of these PMFs. We're going to do it from scratch just so we see what's going on. So the formula is just x times the PMF of x. And when it's y times the PMF of y. And when it's z times the PMF of z. But I just wrote one of those down here. Okay, so let's go through. So for x, it's 0 times 1/2 plus 1 times 1/4 plus 2 times 1/4. Okay, and that's going to be 3/4. Okay, so I can just see that by looking at the plot. I pick up the values of x, multiply them by the heights. So those are the weights that I use, and I just sum it up, and I get 3/4. Let's do the same thing for y. So I'm going to have 0 times 1/2 plus 2 times 1/4 plus 4 times 1/4. And that's going to be 3/2. And that makes sense. It's 2 times the expected value of x by linearity of expectation. So I expected to see the average value of x multiplied by 2. And when I did the calculation directly, I did. Okay, and let's think for a moment before we go to calculate the expected value of x, what should we see? By linearity, it should be shifted over by 1. So I should see 3/4 plus 1, which is 7/4. Well, let's see. I'm going to have 1 times a half plus 2 times a fourth plus 3 times a fourth. And that's going to be 7/4, which is what I thought. So that's the expected value of x plus 1 by linearity. Let's do the variance. So this is our first example where we're really calculating the variance. So I'm going to have the variance formula, which is the expectation of x minus its mean squared. And let's write this out a little more explicitly. So I'm going to have the sum over the range, and I'm going to plug in x minus its mean, which I've calculated, squared times the PMF of x. Okay, so this is actually what's going on. So I need to work out this formula in every case. Okay, so let's see it. For x, I already have the mean, so I'm going to go ahead and write 0 minus the mean 3/4, square it times the PMF 1/2. Okay, so this is what I do at the value x equals 0. I have the value 0 minus the mean 3/4. I square it, and I scale it by the PMF, which is 1/2 at 0. The next one is going to be 1 minus 3/4 squared times 1/4, which is the PMF value at 1. And finally, I'll have 2 minus 3/4 squared times a fourth, which is the PMF value at 2. Okay, so the rest is just going to be some simplification. So I'm going to have 9/16 from the square times a half plus 1/16 times a fourth plus 25/16 times a fourth. Okay, so that's just from working out all those terms. So putting it all in the same scale here, I'm going to have 18 plus 1 plus 25 all over 64. So that's 44 over 64, and that's 11 over 16. So the exact value isn't important. What's going to be interesting is how this compares to what happens in the next examples. Okay, we're going to redo this calculation for y. So the first term is going to be the same, 0 minus 3/2 in this case, squared times a half. So why 3/2? Because the mean of y is 3/2. It is not 3/4. Okay, so every other value stay the same because the value of y is still there at 0, and the PMF value is the same at 0, it's 1/2, but I changed the mean to the mean of y. So now I'm going to go all the way to 2, subtract 3/2, square it times a fourth, and then finally go to 4, subtract 3/2, square it times a fourth. Now I just simplify things. I'm going to get 9/4 times a half plus 1/4 times 1/4 plus 25/4 times a fourth, and that's going to be 18 plus 1 plus 25 all over 16. Okay, so that's going to be 44 over 16, which is 11/4. Does this make sense? Okay, we saw for the variance of a linear function, I should have the a squared times the original variance. So in this case, I have 2 squared times the variance of x, and that makes sense. Let's do it for z now. I have 1 minus 7/4 squared times 1/2. So I have the PMF value, which is 1/2, and that happens at z equals 1. I'm subtracting the mean, which is 7/4. I have 2 minus 7/4 squared times a fourth, and 3 minus 7/4 squared, which is a fourth. And so then things are going to work out to be 9/16 times a half plus 1/16 times a fourth plus 25/16 times a fourth. Okay, again, this is going to work out like before to be 18 plus 1 plus 25 over 64. That's going to be 44 over 64. That's going to be 11 over 16. And hold on, that's just going to be equal to the variance of x. Okay, so what has happened here is I'm looking at basically the same variance because all I've done with x is shifted it over by 1. So the way it varies around its mean has not changed, only the mean has changed. And the variance of a linear function formula does not have any effect from the shift b, and that's exactly what we saw here, right? So I'm just seeing which, how spread out am I around the mean, and that has not changed. Where it changed was with y. So with y, I ended up more spread out. So the values are actually more spread out, and I saw that the variance increased. So that's what happens when I have something that's more spread out. I have a higher variance. Okay, so we're going to wrap up with one more formula that we could use. We'll use it in some later videos for calculating the variance. And it's going to be that the variance is the expectation of x squared minus the square of its expectation. Okay, so the reason we might end up using this formula is maybe we've already calculated the expectation of x squared, and now this is a way of reusing it in case we want to get the variance without having to redo that part of the calculation. Now, let's just see why this is true for a moment, okay? So it doesn't seem immediately obvious, so let's just kind of open things up and see why it's true. So I'll start by writing the definition of the variance. So x minus its mean squared times the PMF of x, and so I'm using mu x to represent the mean. So I'm going to open up the square, okay? So I'm writing out the square, and what I'm going to do is write each term with its own summation. Okay, so I've opened this up into 3 separate summations. And this is where things get a little bit interesting. So now the first term, from what we've done already today, is going to look like the expectation of x squared. The second term, I'm going to keep 2 mu x aside, and notice that that's being multiplied by something that looks like expectation of x. And this third term, I'm going to keep mu x squared out, and I'm going to notice that this is really just 1. Why is it 1? Because of normalization. If I sum up the PMF, I get 1. Okay, so now I'm going to plug back in for mu of x, because mu of x is just the mean. So I get expectation of x squared minus the expectation squared times minus 2 plus expectation squared. So then the minus 2 and the plus 1 here cancel out a little bit to just get minus 1. So I get the formula that I had above. Okay, so we'll see some applications of this in a later video, but we've kind of gone on the longer side here, so we're going to just wrap up. The only thing I want to mention to you is a little bit more terminology, which is that sometimes we call the nth moment this thing which is ex to the n, and the nth central moment ex minus its mean raised to the n. Okay, so you might see that that kind of terminology thrown around. I might say it from time to time, but that's just something to have in the back of your head.